All right, welcome back. So in the last video, we were looking at the sort of bird's eye view of two sample t-tests. Pretty cool, pretty all right. We got an idea of the process, but now let's actually kind of break it down, do it a little bit slower so you can get an idea of what's going on. Super similar to the one sample t-test as far as the process goes. I've been saying that all this time. We just have slightly different formulas that we have to use. So let's just get into it. So you can pause the video and read this yourself, but the long and short of it is we've got two different types of bees, and we want to figure out if the time they spend at flowers are statistically significantly different between the two species, right? So we have berry bee and the bee from Honey Nut Cheerios. So berry bee is a bumblebee, and obviously the guy from Honey Nut Cheerios is a honeybee, so it only made sense. But we've got all of the information here. Actually, we have all of the information here. So here's what we know. So these things are measured in seconds. So we found that, let me zoom in here too. The sample mean of the bumblebees, they spend on average 16.21 seconds. I should probably write that. At flowers. And then with a standard deviation, a sample standard deviation of 10.16 seconds. And there was 34 in this group, 34 bees that they looked at. Okay, and then for the honeybees, their sample mean was 35.83 seconds, and there's with a sample standard deviation of 23.23 seconds. So I'll write that too, seconds. These are all in seconds. And then these only had 12 bees in the sample. So not a whole lot, but we'll assume that this is all decent, right? This is all okay. That difference between the two is fine. Okay. So what do we need? Well, we need first to find the t-stat, and then we'll find, what the heck? We'll find the confidence interval too. I'm not even sure if it asks. No, it does not, but let's just do it anyway, right? Also, we'll assume that this is going to be, an alpha of 0.05, so that confidence level will be 0.95, right? Sweet. Okay, now I've realized, so I actually did this whole video already, and I realized that this blue, there's no color that fits well in this background. That's my bad. So I'm just going to do it all over again on a better piece of paper here. So let's just get into it. So the research question is already written. Are the time spent at flowers statistically significantly different between the two species? Okay, so that's step one. Step two is the hypotheses, right? Very cool. Very cool. Okay, and so we have our two usual suspects, right? However, I'm going to write them in two different ways, just so we can kind of see what's going on. Okay, so same deal. They're both going to be saying the same thing. Oops, be consistent. Both going to be saying the same thing. Okay, so effectively what we're trying to do is, based on these samples, we're trying to kind of elevate them back up to the population of bumblebees and the population of honeybees, right? Two separate populations. So in this case, we would maybe say that our null hypothesis is that there is no difference, right? That there is no difference between the bumblebees, the mean time spent for the population of bumblebees at flowers is equal to the mean time spent at flowers for honeybees, right? We're saying that there is no difference, right? They are exactly the same, okay? Even though we see that the means are very much different, but there's some overlap here with the standard error. Do we have enough evidence to suggest that, this difference is actually true? So then the alternative is what I just said, that the population of bumblebees is not equal to the time spent for honeybees, right? So we're not saying anything about direction. We're not saying anything about anything. We're just saying, is it different, right? And then we go out, collect data to support. Okay, so that's one way of writing it. That is one way that you've seen it, or that is the way that you've seen it. But we can also kind of move these around, kind of algebraically, to get some new sort of terminology going on. Not even terminology, but just a little bit of a different frame, right? So we can even say that since we're looking at differences, assuming that, these two are the same. That means if we subtract the two, it's going to be 0, right? This is saying the same thing that this is saying, right? That the difference, the straight up difference, the literal difference, the mathematical difference between the two is 0, right? Same thing here, right? Because you can move this over, and then that means there's a 0 right there. Same deal, right? And then same deal here, slightly different frame. Does not equal 0, right? So the difference between these two is going to be some value, right? It might be close-ish to here, right? So depending on which one makes more sense to you is, you can use that one and it's totally fine. If they both make sense to you, that's also great. You'll see it written both ways. I like this way because we're working with differences, right? Kind of makes sense. But oftentimes people will show it like this, and I think a lot of textbooks do it too, to where, this is saying that they're equal or they're not equal. This is saying that the difference is not there and the difference is there, right? Same thing, just a slightly different frame. So you'll see that kind of frequently. Okay, so that's step 2. Step 3, we got to find this test statistic, right? Tests, so step 3. Test statistic. Oh my god, I almost did it again. Stastic. I am an idiot. Okay, I promise I know how to write. I speak English, more or less. Okay, so all we really need to do is take this thing, right? Bring it down here and fill in the gaps, right? So let us do that. So T. Also another thing, this is just me. I try not to write my T's like this. You might be able to tell the difference, but when we get into like addition, to me they look totally the same when I write them. So I try to give this T this little swoosh, just so we know. Anyway, that helps me. It took me forever to figure out a good way to do it. Okay, anyway. So we're subtracting here, right? We're going to be subtracting two means, right? These two means. Ideally, I would like to work with positive numbers. So let's take the larger number and subtract the smaller number. Just kind of makes sense, right? Regardless of which way you do it, the outcome will be the same. But I find that working with a positive sign is much easier than keeping track of all the negative stuff. So we're going 35.8, right? We're going to say that honey equals x1. I'll write this up here just so I don't lose track. Bumble equals x2. Very cool. Okay, so that's 35.83 minus 16.21. All right. And then the standard error formula, right? Or just the denominator, if we're just trying to take it kind of one thing at a time. We got to take sample standard deviation of the first one and square it, right? And that brings us to the sample variance. Okay, so no biggie, just technically that's what's going on. You could go your whole life with knowing that, without knowing that, right? I'm okay with that. So so here's what I'm sort of doing too, splitting this up between the honey, or I guess 1 and 2 kind of situation, right? Just so I can keep track of things. Anyway, so that's squared divided by, and then we got 12 people in the honey, 12 people. We got 12 bees. Honeybees. Okay, and then we've got 10.16 squared divided by 34, right? So now the order in which you add these together does not matter, but the denominator of these things, they do matter, right? So you want to make sure that you've got, and I'm going to double check here, I've got the bumblebee here and the bumblebee sample size, right? Because if these switched, that's going to be two totally different things, right? Okay, so final touch. This is all underneath the square root sign. Very cool. Very cool. Okay, so I've already got this worked up. Let me just, that's right, okay. Clicked a couple of buttons on my computer. Here we go. So we get a test statistic once you run all that. You get a test statistic of 2.82. So let's highlight that so we don't lose track, right? So we don't lose track. Very cool. Very cool. Okay, so that's what is that? Step 3. Sweet. So I've got room down here. Let's do step 4. Step 4. And that's the p-value, right? So we're just going to plug in. Thank God for the computers, honestly. We're just going to plug this in into our thingy, right? Oh, and one thing we also need to do is let's figure out the degrees of freedom, as I just saw it there. So the degrees of freedom is going to be the n minus 1 of, right? This is kind of the asterisk here. Smallest n, right? Right. Okay, so glad we're on the same page. So in this case, our smallest n is not 34, but it's 12. So 12 minus 1 is 11. Neat. Okay, so we come up in here. I'm going to get rid of this just so we can kind of see what's going on. Great. So we plug in that, and it draws the curve for us. Very cool. And then we just plug in our test statistic in the two-tailed option, right? Because we have no directionality. And here we are. It turns out that our p-value is going to be 0.016. 0.016. Very cool. So I'll just come back here. So p-value equals 0.01. Actually, I think there's another 6 after that. Yeah, so we'll just say 0.017. Not like it really, it doesn't really matter so much that that 1 decimal point there. Okay, so now we have our p-value. Very cool. So now we can go onto the next page and make a conclusion, right? So first, I think step 6. No, wait, step 5. Yeah, step 5 is sort of like the mathematical conclusion, right? So we'll just kind of put them both in the same thing, because then we're gonna kind of translate it into English, right? So our alpha is 0.05. Our p-value was 0.017. Yes. Very cool. So what do? Well, p is less than alpha. So we're going to, let me write it over here in a different color. We're going to reject H naught. And now let's recall that H naught is mu bumble equals mu honey, right? So we have enough evidence. We have quite a bit of evidence. This is a pretty low p-value. We have, enough evidence to say that these two populations are not the same, right? They are statistically significantly different, right? For the time they spend at, do you hear that crow? Golly. There's like a crow nesting in a tree next to my house, and they just really go at it. Anyway, we have enough evidence that bumblebees and honeybees, on average, for the whole population, don't spend the same time at flowers, which is pretty sweet. So we can write that out too. Let us do that. So step 6. Other conclusion. English conclusion. Whoops. Okay. We have we'll say significant evidence that bumblebees, cute, and honeybees, so cute, honeybees, do not spend the same time at flowers. That's right. Or we can kind of say, that's one way of saying it. We could also say there is a statistically significant difference between time spent at flowers. There's a statistically significant difference between time spent at flowers, between honeybees, and Bumblebees. Now, bumblebees. Very, very cool. If you can read my chicken scratch there, I was saying it slowly out loud, but essentially these two things are saying the same thing, right? We've got the more sort of legal speak here, and then this is the more statistical speak, right? But the overall thing is saying that, on average, the two populations are different, which is pretty sweet, right? But that only asks, or that only tells us that they are different. We got to figure out by how much, right? So let's do that. Let's make a 95% confidence interval for that. 95% CI. Okay. And let me come all the way back here, all the way back here, and grab this just so we have everything. Boop. Cute. Nice. Okay, cool. Okay, so we've got all that. Very cool. So what do we need? Well, we need X. Come on. I'm going to use a different color. So we need X bar 1 minus X bar 2. And we found that was, let me run it, 19.62 seconds. So the difference, the average difference, so the difference between the two means is 19.62 seconds. Okay. Then all we need, well, the standard error, well, that's just the denominator of our test statistic, which is pretty sweet. That turned out to be 6.95, right? And you can see that if you were to just take this and work it out. In fact, let me just do that. It's going to be a little bit cut off, but you get it. Can I grab this? No, that's okay. So anyway, that's that's the standard error, which is 6.95-ish. I'm kind of rounding there. That's okay. So all we need now is the T crit. That's all we need, right? And so our alpha is 0.05. We have 11 degrees of freedom, right? Based on this one, right? Step 4 there. Cool. So we'll just come to our thing. We'll get rid of the test statistic. Actually, we'll just start anew so we can make sure. See, it takes away the curve. So we put in 11, draws the curve, and then all we need to do is put in 0.05, and we get a test statistic of 2.2. 2.2, which is pretty sweet. Okay. So let me write this out. Let me write this whole thing out. 2.2. Okay, so our lower bound, what does that look like? Well, it's just going to be, what is it going to be? Let's see, it's going to be 19.62, the lower bound, right? So we're subtracting, times 2.2, sorry, minus 2.2 times 6.95, right? Very cool. Okay, so let me see. Let me get my old calculator out here. 2.2. Sorry, I've got it. Very cool. Very cool. Okay. Let me double check. Sorry, I'm doing a lot of. Actually, you're gonna hear me type a bunch here in just a second. You can fast forward through this. So 19.62, I just want to make sure I've got this. Okay, and then 2.2 times 6.95. Very cool. Yeah, dope. Okay, I was right. Okay, and then, so that turns out to be 4.33, and then we'll put seconds there, right? Okay, and then the upper bound, same deal, we're just adding though. So it's 19.62 still. 0.62. And then times, or sorry, plus, good lord, plus 2.2, right? I'm kind of drawing the parentheses out here, right? Just so you can kind of see how the order of operations there goes, right? We multiply these two together first and then subtract, right? Or multiply these together and then add. So you're not doing these first, whatever. Okay, so beautiful. You're hearing me type a bunch. Sweet. Okay, so that turns out to be 34.91 seconds. Very cool. Okay, so let's go over here and let's write this out, right? So our 95% CI, actually we'll just save the equals, was 4.33 to 34.91. Very cool. Okay, so what is this for, though? This is not for the mean anymore. This is not for either one of the means. This is not for the mean of the honeybee or not for the mean of the bumblebees. But this is the 95% confidence interval for the difference between the two populations. Okay, so in this case, we are 95% confident. What the heck? 95% confident, English, that the true difference, the true mathematical difference, straight up, if we got both populations and took their mean and subtracted them, right, we are 95% confident that the true difference is between 4.33 seconds and seconds and 3.91 seconds. Okay, so now that's a fairly large interval, right? That's a pretty big 4.33 seconds. We have evidence to say that that's statistically significant, whatever. But maybe to what do you call people who study bugs? Is it etymologist or is it entomologist? One of them is words and one of them is bugs. Whatever. To somebody who studies bugs, 4.33 seconds might not be notable, right? They really might not care about that, right? To me, that's pretty small, right? So that is statistically significant, but it is not, it might not be practically significant. It might not be that notable. However, when we go to the other end, though, this is a fairly large difference. And I think, what was our mean difference? 19.62. Yeah, so let me just kind of write that here so we have it. 0.62, I think. Yep. So it turns out that we can get a fairly large range here that is mathematically, statistically significant. But to somebody who studies this stuff, it might be this end that is more, to them practically significant than maybe this end, right? Now, if we had, say, a larger sample size, because we're going up on a pretty conservative approach here, taking the smallest sample size for the degrees of freedom, right? We're assuming that, there is sort of less room to wiggle by taking the smallest. We do that, one, because conservative approach. Two, the math is a lot more difficult, way more difficult. If you assume that there are more degrees of freedom, whatever, no big deal. But what we're saying here, lastly, is that if we had more stuff, right? If we had 100 bees in both, right? Then this confidence interval, we know, will go up, right? Not go up, sorry. It will become narrower, right? This thing will get sort of closer to this value, right? And provide us with a better sort of estimate as to what the difference of the populations may be, right? Looking at differences between two things. Okay, so that is that. So we've got one more type of t-test, super similar to what we've been doing. And I guess I'll just see you there in a little bit.